Hi, today I'm going to talk about the new construction of ALE spaces via gauge theory. So first of all, what are ALE spaces? ALE stands for asymptotic locally Euclidean. For each finite subgroup gamma of SU2, there is an ALE space except gamma corresponding to gamma, where X sub gamma is diffeomorphic to the resolution of singularity of C2 mod gamma. Turns out that every ALE space arises this way. ALE spaces are first classified by Kronheimer in his PhD thesis. He constructs them through a hyperkähler reduction on a finite dimensional vector space, and hence all ALE spaces are hyperkähler, which make them very interesting and rare. There's also this interesting relation of ALE spaces with the Makaya correspondence given by the following statement. So for finite subgroup gamma of SU2, the blow-up diagram obtained by resolving the singularity of C2 mod gamma is the same as the Makaya quiver of gamma. In other words, the irreducible representations of gamma correspond to the irreducible components of the exceptional set when you resolve the singularity. So what I did is that I was able to construct this new construction of ALE spaces using ideas from gauge theory. And here is a construction. So first let gamma be a finite subgroup of SU2, and let R be the regular representation of gamma. Let V be the endomorphism space of R, and then consider E gamma, where E gamma is defined to be S3 cross V mod the relation where PV is equivalent to GP GV equivalent to gamma P gamma V for all G in S1 and gamma in the finite subgroup. So we're thinking of S3 as a S1 principal bundle over S2. And so hence this construction makes E gamma an orbifold bundle over S2 mod gamma with fibers V. And then now we introduce a configuration space. So let AF be the space of connections where you have A plus beta, where A is a gamma invariant connection, Hermitian connection of the hyperplane bundle over S2, and then beta is the one form over S2 mod gamma with values in F mod T. And then our gauge group is given by the base S1 gauge group, the base gamma invariant S1 gauge group, and then the F gauge group, which is also gamma invariant. So they're given by these two spaces. And then it turns out that the gauge group will act on the space of the configuration space AF cross the C infinity sections of E gamma by the following action. And we also have that the space of sections is an infinite dimensional space with 3 Kähler forms. In other words, it's hyperkähler, and then the 3 Kähler forms are the following. So with the previous setup, we're able to write down the following equations. So these are the equations. We can think of them as the moment map equations coming from the gauge group action. So and then the theorem is the following. Let zeta be zeta 1, zeta 2, zeta 3, where for each I in 1, 2, and 3, zeta I is Ci times the volume form, which makes zeta I a 2 form in over S2 mod gamma with values in F mod T for some constant Ci in F mod T. So then let X zeta be the pairs in the configuration space that satisfy the previous equations, and then you quotient out by the gauge group action. Then for suitable choices of zeta, X zeta is actually diffeomorphic to C2 mod gamma, the resolution of singularity of C2 mod gamma. And so we've been able to recover all the ALE spaces through this construction. And then the proof uses this key lemma, which shows that there's this identification of the symplectic reduction with a complex GIT quotient. And the proof is modeled on Hitchin's proof because in his paper, he also needs a similar statement. And then by the key lemma, we're able to reduce our construction to Cronheimer's construction and hence draw the desired conclusion. Thank you.